Okay, so we are looking at intermolecular forces. So our intermolecular forces are going to be the forces that stick two molecules together. So here, again, it's going to hold two or more molecules together. They are not as strong as something we call an intramolecular. So an intramolecular attraction or force is something that holds the compound itself together. So the intramolecular is within the molecule, whereas the inter is between. So sometimes I like to think of these as interstates. So you may know our interstates, like Interstate 5, you can get on it here, you can go all the way up to the Canadian border. So an interstate goes between the states. On the other hand, we can have state routes. So I believe the 60 is a state route, so that means it's only within California. You don't get to go outside of the state on that freeway. So inter means between, intra is within. So just another analogy to help with that is this very adorable girl, which is absolutely not me. I was never that cute. She is trying to eat all those Oreo cookies, and I am hearing you can't talk. Oh, okay, I'm sorry. Try again, Clinton. Can you talk now? Oops. Let's see, can I, anyone want to try talking?
Hello?
Okay, oh, I can hear you now. I'm so sorry.
Yeah, that's fine. No, I had a question about chapter 10.
Oh, okay, yeah.
Before you started. So the hybridized orbitals, you know how it was like an s orbital and a p orbital creates two of those hybridized orbitals,
Yes.
the purple ones?
Yes.
So I was wondering why I think it was two p orbitals and one s orbital. Why didn't it make four of those purple ones? Why was it only like three?
Let's see. So, okay, so you're talking about the hybridizing of, so not the MOs, but, okay, so say that one more time. The hybridizing of.
Because you know how for one s orbital and one p orbital makes two of the purple orbital thingies.
Yes.
Why is it that when you have one s orbital and two p orbitals, it doesn't make four? Like it only makes three.
So we always get back the same number that we put in. So here we have one S and two P's. We get a total of 3 because we have 1, 2, 3 to start with.
Oh, okay. Yeah, that makes sense.
Okay, excellent. All right, so I apologize.
Right, thank you.
Oh, you're welcome. I apologize. Looks like I had my speakers plugged in but turned off. That was a problem with the sound. Sorry, still getting used to the computer setup here. Were there other comments or questions that I missed? Okay, so it sounds like just that one. So I apologize, Dervin. And thank you, everybody, for jumping into the chat to help Dervin with this question. Okay, so next up, the intermolecular forces. So let's say you're a little kid like this girl, and you want to eat all those Oreos at once, and you're trying to shove them all into your mouth. You know what's going to happen. That whole column of Oreos is going to go flying because there's nothing to stick them together. There's no intermolecular force. So let's say you want to shove them all into your mouth at once, but you're worried they're going to fly away. What you could do is make something like this Oreo cake. So here you're using that frosting as something to stick all the cookies together. So this frosting here is acting as the intermolecular force. It's allowing us to stick more than one Oreo together. And that way, if you shove that whole cake into your mouth, in theory, it's not going to go flying because it's all stuck together. All right, so yes, I'm a sugar addict. But just another example of the intermolecular. It's sticking more than one thing together so that if you were trying to, say, shove all those Oreos into your mouth, they will not fly apart. In terms of our molecules, when we're talking about a solid, when we're talking about a liquid, they need to stay together. And the only way they're going to stay together and not fly apart like those Oreos are just about to do is through the intermolecular forces. So the intermolecular forces, overall, they're pretty weak. They're much weaker than anything we've talked about thus far. They're weaker than the covalent bond, which can create the diamond. They're weaker than the ionic bond, which can create that NaCl that I've told you a couple times. It melts at over 1,000 degrees Celsius. So intermolecular force is much weaker than any of those things. However, they really make our world go round. They allow us to have solids. They allow us to have liquids, things like surface tension. So they're absolutely essential both in the human body and in the world, but they are extremely weak. They're about as weak as that frosting, but that frosting helps everything stick together. All right. So again, these intermolecular forces are extremely weak. However, they are strong enough to control physical properties like boiling and melting points, vapor pressures, and viscosities. So just to give you one more analogy of what we're talking about. Thanks. And there it is. All right, so I have a rubber band here. So this rubber band is relatively weak. I can't really use this for like weightlifting or really anything very strong. If I put enough strength into it, this is going to break. So relatively, this is weak. But now what I want you to imagine is 1,000 or 1,000,000 of these rubber bands all tied together. This could make a net strong enough to hold somebody as large as I am. It could be a trampoline for a really heavy person like me if you had enough of these. So individually, these intermolecular forces extremely weak. However, with enough of them together, we can change the properties of these chemicals. So any questions on anything so far? All right, so again, these are the forces that are going to hold the molecules together, and we're going to talk about 3 types. So first we have our dipole-dipole interactions. And if you remember from way back when, if something has a dipole moment, it is polar. So dipole-dipole means that we have 2 polar molecules. So another way to talk about this is polar-polar. And when I say polar-polar, I'm not just thinking about food, pizza. I'm thinking about 2 molecules, both of them being polar. That's what we mean by dipole-dipole. All right, so next up we're going to talk about hydrogen bonding, and finally the last and kind of the trickiest one, which we think of as London dispersion forces, and I like to think of them as temporary dipoles. They're going to be molecules that are polar but only for a moment, so temporary or instantaneous dipoles. And we're going to go through each one of these. But any questions so far? All right, so starting with our dipole-dipole forces. So again, a dipole means there's a separation in charge, and that is another way of saying you have a polar molecule. All polar molecules have a dipole-dipole force. Some of them also have other things like hydrogen bonding, but all of them have a dipole-dipole. So again, it happens in all polar molecules. Anytime there's a partial positive and a partial negative charge. And our example is our formaldehyde here, so CH2O. And what we learned way back when is that oxygen is more electronegative than hydrogen. So if I were to draw an arrow, I would say the electrons are flowing towards that oxygen and away from the hydrogen. Because the electrons are flowing towards oxygen, it makes it partially negative. Because the electrons are flowing away from this carbon and the hydrogens, this whole end down here is going to be partially positive. Okay. So first of all, any questions on why this molecule here is polar, how I drew that arrow, or those partial positive and partial negative charges? So just to remind you from last class, this delta looks sort of like an 8, except it's missing this little piece right here. And this is delta. It's a lowercase d, so here it doesn't mean charge, it means, it doesn't mean change, it means partial. So here we're saying the oxygen is partially negative and the carbon and hydrogens are partially positive. Mhm.
What was the triangle symbol from? I think from the heat. Would that be delta also, or was that a different one?
It is. So in Greek, just like our letters have a capital and a lowercase. Just like our letters have uppercase and lowercase, so did they in Greek. So here, this is a capital delta, and this means change. And this is a lowercase delta, and it means partial. And just for fun, in case you ever wanted to try it out, you do capital D and you change it to symbol. On your computer, you're going to get the triangle, and if you do lowercase d and you change it to symbol, and the symbol is the font symbol, you're going to get that. So yes, so we have capital delta and lowercase delta, capital meaning change, and lowercase meaning partial.
Okay, thank you.
Oh, you're welcome. I know not everybody's as nerdy as me, but when I was a student, I always thought it was really fun to be able to type chemistry stuff on something like Microsoft Word and actually have Word give me the actual symbol. So anyways. Okay, so any other questions about what we've done so far? All right, so the idea of the dipole-dipole force is we have the same thing that we've talked about in the past, and let me actually go back for just a moment and remind you of what ionic compounds do. So in an ionic compound, something like NaCl, we have a positive and a negative, and what I told you is that they are not actually bonded. There's no true chemical bond, there's no sharing of electrons. What it is an attraction between the positive and the negative, and we called it an electrostatic attraction. And that is just to say that the reason they're attracted to each other is those charges. So sodium is attracted to chlorine, and chlorine is attracted to sodium. And the reason that we can have ionic compounds that are huge crystals like you would see in a cave, or like a geology teacher might grow in his kitchen for fun, his or her kitchen for fun, is that they don't discriminate. So positives are attracted to negatives, negatives are attracted to positives, and we can just keep on going forever. So it is purely based on the positive and negative charges. And this right here is an ionic compound. And it is ionic because there's full charges. So it's a full positive and a full negative. The dipole-dipole is almost the same. It's just that instead of a full positive and a full negative, it's going to be a partial positive and a partial negative. So here, the negative on one molecule will line up with the positive on another, and it will create an attraction. Same kind of attraction you would see right up here with the NaCl's. The difference is it's just not as strong as the ionic compound, but it is still electrostatic attraction. So it is still a positive and a negative being attracted to each other's charge, but here, because it's a partial charge, it is now a dipole-dipole force rather than an ionic bond. So again, exact same thing, just not as strong because we don't have a full charge. And this follows what we learned about our lattice energy. We said that if they had greater charges, they're more attracted to each other, so they would have a greater lattice energy. So a 2 plus and a 2 minus would be stuck together better. And so if you want to pull it apart, it would be harder. You'd have to put in more energy. So the greater the charge, the more they are stuck together. The lesser the charge, the easier it is for us to pull them apart. But they're all operating off the same type of electrostatic attraction. The same thing, positives and negatives being attracted to each other. So any questions so far about the dipole-dipole force and how it's similar to the ionic compounds that we've looked at before? Okay, so here I've only drawn 2, but I could draw any number of them. And in fact, there are millions, billions of these in a solution. And they are going to be attracted to each other just like the ionic compounds were. So I could draw another one here. And because the oxygen is partially negative, this back end is partially positive. Oops. Green. Again, we're going to have the attraction going on. Like so. So you can just draw this forever, and you can keep joining negatives and positives. And in fact, in your homework for this chapter, I ask you to draw, not a million of them, but I believe I ask you to draw like 4 of them or maybe 5 of them, just showing that the positives and negatives are always attracted to each other. And in fact, if you're ever like thinking, hey, my kid needs a fun art project, they're home, they don't know what to do for this summer, and they're like, I want to color, what can I color? Show them how to do the intermolecular forces. Not only do they get to show off their artistic abilities, but they get to learn some science. All right. But any questions about this idea of the dipole-dipole forces and how the positives and negatives are attracted to each other through that electrostatic attraction? All right, so now let's go ahead and take a look at some of the consequences of the dipole-dipole interaction. And this right here is our dipole moment. It's got this symbol, it looks like a U, it's actually called a mu, which is very funny for us cat people. And so here is the unit, so D, dBi. And our dipole moment, as I've mentioned, is a measure of how polar something is. So I'm sure I've told you the joke, but I'm going to tell you one more time. So 2 molecules are sitting in Starbucks, and one is saying, dude, I'm so polar, and the other one's like, oh, not even, I'm so much more polar than you are. And the first one says, oh yeah, let me see your dipole moment. So these are those dipole moments that I was talking about. So these dipole moments tell us how polar something is. So remembering that all of this attraction has to do with how great of a charge. If you have a 2+ charge, you're more attracted to your 2- mate than if you had a 1+ and your partner was a 1-. So now that we're talking about partial charges, again, the greater the charge, the greater the dipole moment, the greater the forces between them are. So now, let's compare some of them. So I'm going to go ahead and compare dimethyl ether, which is definitely polar, definitely has dipole-dipole interactions, but it's got a fairly weak dipole moment. Then I'm going to compare it to acetonitrile, which is also polar, also has dipole-dipole interactions. But check out that dipole moment. You could easily see that if acetonitrile was in Starbucks, it would be bragging all over the place, dude, I am so polar. So it has a huge dipole moment. That dipole moment translates into it being more attracted to its neighbors. If it's more attracted to its neighbors, it will have a higher boiling point. The idea of the boiling point is we're thinking about how high do you have to turn up the temperature to break the intermolecular force. Whenever you're boiling, you are actually pulling something apart from its neighbor. So here, we want to rip acetonitrile away from its neighbor. You're going to have to get up to 355 Kelvin, whereas dimethyl ether is 248 Kelvin. So the reason that ether is a liquid, but it is very volatile, it goes into the gas phase very easily. And in fact, if you were to open it in a classroom, everybody would smell it very quickly. And in fact, ether is one of those things that way back when, I think we talked about this a little in chapter 1, it was used to knock people out for surgical procedures. So open it in a room and it won't be too long before people start feeling a little woozy. But it goes very easily into that gas phase because it has such a low boiling point. At room temperature, we are able to separate ether from its neighbor. It doesn't take very much because it's really not that attracted to its neighbor because it has a very weak dipole moment. In other words, it doesn't have very strong charges. Whereas acetonitrile, you'd have to heat it up quite a bit to get it into the vapor phase, into the gas phase, because of how attracted it is to its neighbor. Now, it's nothing compared to NaCl. NaCl, we've talked about, you got to get it up over 1,000 degrees Celsius because it has a full positive and a full negative. But of all of these here that have extremely weak polarity, or I should say they all have polarity, there are some that are extremely weak, like dimethyl ether, and some that are much stronger, like that acetonitrile. So at the bottom it says the more polar the molecule, the higher its boiling point. This is something we're going to see throughout this section, the greater the positive and negative charges it has, the more it is going to stick to its neighbor, just like we saw when we were doing lattice energy. So before we talked about a 2 plus and 2 minus versus a 1 plus and 1 minus, now we're talking about a dipole moment that in this case is a 3.9 versus a 1.3. So if you want to think of it in terms of relationships, the relationship between acetonitrile and its neighbor is steady as a rock. Nothing could separate them. Whereas dimethyl ether, they're into each other, but they could be tempted to stray. All right. So questions on anything so far about our dipole-dipole interactions and how that dipole moment affects properties like the boiling point? All right, so next we're going into hydrogen bonding, and we're still talking about the same thing. We're still talking about charges and molecules being attracted to one another. And I'm going to go ahead and just give myself a little more room here. So hydrogen bonding, and I'm going to look at a water molecule, but I'm just going to put it right above here so I've got a little bit more room. So we know that oxygen is more electronegative than hydrogen. We know that our electrons are going to flow up towards that oxygen, and they're going to be going away from the hydrogens. So up here we're going to have partial negative, and down here we'll have partial positive. Now the reason we give hydrogen bonding a special name is that when we have a hydrogen directly bonded to a fluorine, a nitrogen, or an oxygen, there is something special that happens. So oxygen is extremely strong, not as strong as fluorine, but still very, very strong. And I'm sorry, let me rephrase that. So oxygen, fluorine, and nitrogen are all extremely strong. Hydrogen, unfortunately, is a little on the wimpy side. So when any of these, are like, hey, I'd like to borrow some electrons, hydrogen's like, take them, everybody takes my electrons, what can I do about it? So they're all flowing just like we would see in a dipole, but they flow much more so because you have somebody very strong with somebody very weak. Now normally if you were to have oxygen, nitrogen, and fluorine attached to, let's say, a atom that respects itself a little bit more, when they're like, hey, I need your electrons, carbon might be like, oh yeah, you borrowed my electrons last time. I don't think so. I'll give you a little bit, but not very many. As opposed to hydrogen, who just has some issues, a few codependency issues, and is like, oh my gosh, okay, you can take them all again. Okay, maybe next time you won't take as many, right? So the deal is that you have something very strong with something very weak. It's causing a much greater flow. And so I like to think of hydrogen bonds as dipole-dipoles on steroids. They do everything the dipole-dipole does, but they do it better because there's a greater charge separation. So the way I like to write these is with 2 negatives and 2 positives here. It is still not a full charge separation like you'd see in NaCl, but it is much greater than what you would see from a normal dipole-dipole. And that's why we gave it a special name, because we see unique properties whenever we have these three combinations. The hydrogen-fluorine, hydrogen-nitrogen, and hydrogen-oxygen. And there is a kind of a funny way to remember the 3 elements, the fluorine, oxygen, and nitrogen. So for those of you old enough to remember ET, and you remember ET phones home, sometimes we say hydrogen phones home. So that is just a way to remember that we need a direct bond between either a fluorine, a nitrogen, or an oxygen, like so. So questions on anything so far with these, and this is all our hydrogen bonds I'm talking about? Good question, Clinton. So these all must have must be polar molecules. So yes, it must be polar molecules. However, when you have this combination, I can't think of anything that would not be a polar molecule. The one that I'm thinking just off the top of my head would, this does form a tetrahedral, but it's an overall positive charge. But I can't think of anything else that would form a symmetrical shape and have identical elements on the outside. Yeah. And then I see another question. Is it only with those three elements or anything bonded to hydrogen? It must be very specifically these elements. And that's why this is a nice way of remembering it, that hydrogen phones home. You must have a direct link between the hydrogen and the fluorine, hydrogen, oxygen, or hydrogen, nitrogen. And it is only these. So sometimes students ask, well, why can't we include chlorine? Because chlorine has the same or almost the same electronegativity as nitrogen does. However, we know experimentally these are the only three elements we've ever seen it in. And so that's why we just say memorize those three elements. That's the only thing we have any experimental evidence where it happens. Okay, so just for fun, I'm going to go back just a moment here. We just looked at this molecule right here. Why can't the one I just drew, and I'll put in its lone pairs here, why can't this one hydrogen bond? It's got oxygen and it's got hydrogen. Why can't this one hydrogen bond? They aren't together, so yes, the hydrogen is not bonded to the oxygen. You do not have a direct bond here between the oxygen and the hydrogen. So we know that oxygen is very greedy, and we know oxygen is going to try to pull electrons. And we know that hydrogen is not the strongest in the world. It's working on its issues. It's going to therapy right now. So oxygen's like, hey, hydrogen, give me your electrons. And hydrogen's like, okay, but it's got a carbon in the middle. And that carbon is like, hey, none of this. Oxygen, you behave yourself. So we still have the partial negatives and the partial positives, but they are nowhere near as strong because that carbon is in the way. That carbon is acting like a mom, a dorm parent, whatever you want to say, saying like, oxygen, you treat hydrogen nicely. So oxygen cannot pull that many electrons from the hydrogen because carbon's in the way. It still does try, it still gets some, but not nearly as many as what we would see down below here, where you'd have it directly bonded. And I hope you guys don't mind my silly analogies. But questions on anything so far? So I'm going to put a label by this one, and I'm going to call this one the dipole-dipole. Okay, so any questions on anything thus far, including why this H2O cannot hydrogen bond? Excellent. Okay, so let me zoom into this right here. So what we're seeing here is on the top, we're seeing our water molecules, and we're seeing their hydrogen bond right here. So a hydrogen bond, again, it's always between two molecules. Now, a lot of students kind of get turned around because when we say hydrogen bond, it sounds like we're saying, well, hydrogen is bonded to something, and they want to identify this as the hydrogen bond. That bond that I just colored in blue is required in order to have hydrogen bonding, but it is not the hydrogen bond. This is our hydrogen bond. Remember, a hydrogen bond is an intermolecular force. It is always between two molecules, and that is why this one right over here cannot be a hydrogen bond. This right here is our covalent bond. So it's a bond created by sharing of electrons. The hydrogen bond is only an interaction between positives and negatives. So any questions between those two bonds, the one that I have highlighted in green there and the one that I colored in blue, about why the green one would be the hydrogen bond and the blue one would be the covalent bond? All right, so just to take a look at one more, and this time we're going to look at the one below. This is ammonia, NH3, and we see the same thing. So right here in between the molecules, that is our hydrogen bond. The one right over here, this is just a covalent bond. So when I say covalent bond, I mean these are the kind of bonds you made when you're doing your Lewis structure. They are truly shared electrons. Hydrogen bond, we don't have actual electrons being shared. We are just have an association, an electrostatic attraction between, in this case, our partially negative nitrogen and our partially positive hydrogen. So they are attracted to each other, but it's not a true chemical bond. Here, they did it with dots. I try to avoid dots because we have Lewis dot structures. So I would probably have drawn it if it was me, I'd draw it sort of like this instead, rather than the dots, or preferably, probably, since I had access to a highlighter, I would use a highlighter. So yeah, it's just an artistic choice to do the dots. All right. So any questions so far about these two, the water and the ammonia? Sometimes when we do things in chemistry, we're like, oh, this looks so cool, and we forget that students who've just learned Lewis dot structures now have to deal with more dots, and it's mind-blowing, but sometimes from the perspective of the illustrator, we don't always think of the student's point of view. All right, so hydrogen bonds are unusually strong dipole-dipole interactions. And again, I like to call them dipole-dipole interactions on steroids. So they occur when hydrogen is bonded to an unusually strong electronegative atom, and where we see it is with our nitrogen, oxygen, or fluorine. It needs to be a direct bond, but again, be careful. It is not that bond, that's the hydrogen bond. So let me just say that one more time, because this is kind of a point that a lot of people get turned around on. So the hydrogen bonding can only occur if you have nitrogen, oxygen, or fluorine bonded to a hydrogen. But that itself is the covalent bond. If you have this right here, you can now form a hydrogen bond, but the hydrogen bond is this guy right there. So this is necessary so that you can have this, which is the hydrogen bond. So any questions on that? I know it's kind of a tough thing to think about, that you need this for a hydrogen bond, but that is the hydrogen bond. Okay. All right, so what's going on is we have a much greater dipole. So in other words, we have a much greater positive and negative on these molecules, and so their electrostatic attraction is just greater. So it's not as great as an ionic compound, but it's much greater than your typical dipole-dipole. All right, so here's a graph just showing how dramatic hydrogen bonding affects the properties of these molecules. So here again, we're looking at boiling point. And what we expect is as the molecules get a little heavier, the boiling point goes up a little bit. That heavier, larger molecules tend to be more attracted to each other. So here's a nice, fairly steady increase. But when we get to the one above, this is what we would have expected, but water is way up here. And the reason is, again, because of the hydrogen bonding. So water has that hydrogen bonding, so has a much greater positive and negative. Therefore, it's going to stick to its neighbors much more so than something with a simple dipole-dipole. So if you want to separate water from its neighbors, you're going to have to put a lot more energy, a lot more heat into it because of that strong electrostatic attraction, because we had a very electronegative atom connected to a very wimpy atom, if you will. Sorry, hydrogen. But any questions on this, that hydrogen bonding dramatically affects the properties of these molecules? So I know every science teacher, every scientist thinks their subject is the center of the universe, and I am no different. So when I think about hydrogen bonding, I actually think about what makes the world go round. And so if water did not have hydrogen bonding, water would have a boiling point somewhere down here. Now imagine we have all of our oceans. Every day when the sun came out, we have plenty of heat for the entire ocean to vaporize into the gas form. And then at night, and when it cools off, and it would actually have to get very cool, but if it gets cool enough, it would all rain back down the entire ocean. So the only thing that keeps our oceans where they're at is the hydrogen bonding. So the hydrogen bonding allows us to have a high boiling point, high heat of vaporization, and it allows us to keep oceans on Earth. So without hydrogen bonding, life on this planet wouldn't be possible. So just a little thing about why chemistry is your most important class. I'm kidding. All right, but questions on anything here? I always think about how crazy it would be if every day when the sun came out, all of the oceans evaporated, and then every night when it cooled off, the entire oceans rained back down on the Earth, and how we could not survive that. So hydrogen bonding allows us to keep water in the liquid phase because it has that high boiling point and it can stay liquid. Okay, so any questions about dipole, or hydrogen bonding? So before we move on, I just want to emphasize one more thing. Earlier we said all polar molecules have dipole forces. So all hydrogen bonded molecules also have dipole forces because they are polar. So I'm going to say here every molecule, oops, all right, so every molecule that can hydrogen bond also has dipole forces. Now we often don't talk about it because when you're dealing with something like water, we often talk about only its strongest force, which is hydrogen bonding. But it also has dipole interactions. So again, every polar molecule, including every molecule that can hydrogen bond, has dipole interactions. It's just that if you can hydrogen bond, you have both of them. So any questions on that? Okay, let me give you a moment to copy. All right, I went ahead and threw up that poll, so go ahead and click in if you'd like more time or if you're ready to move on. Just if you need more time to write this down. Okay, so it looks like a few people need some more time to write it down, so go ahead. Any questions on anything we've talked about so far with our hydrogen bonding or our dipole interaction? All right, I'm going to go ahead and relaunch that poll, so because I don't want to move on if someone still needs this page. So anyone still need this page, just go ahead and click in yes if you'd like more time, or no if you're ready to move on. Okay, so it looks like everybody's ready. All right, so next up is London dispersion forces, and I like to think of these as temporary dipole-dipole forces. Sometimes they're also referred to as instantaneous dipole-dipole forces. So here's the deal. We have some things that we call nonpolar, and they might be individual atoms, they might be molecules, and they are supposed to be nonpolar. They are supposed to behave themselves. And in fact, if you saw a helium atom like this, you might think, well, why are both electrons on the same side? They're supposed to be spread out evenly because electrons repel each other. So what we would think of is that this electron is in the wrong place, and it should be right over here. So they should be spread out, and this is the way they are most of the time. But every once in a while, just for an instant, and when I say an instant, I don't even mean a second, I mean like a nanosecond. Very, very suddenly, they are on the same side. And they're not supposed to be on the same side. We have labeled it as nonpolar. We've said, hey, we looked at our geometry, we read our rules, and you are nonpolar. And helium says, well, not right now, I'm not. I'm having one of my days. So just for a moment, something that's supposed to be nonpolar can be polar. So again, it's just an instant, but it happens. And then the question is, well, why? Why would something ever become polar for an instant? If you look at those electrons, they are not supposed to be near each other. They have electron-electron repulsion. This is a high energy state. It should not exist. So I'm going to use the example of this cup of water right here. Oops, there we go. All right, so if I'm holding it nice and steady, the water's not moving too much. But now I'm going to imagine that I was a waitress, and I would never do that because I'm very clumsy, but the water's going to start bouncing from side to side a little bit as I walk across the room. That's what's happening in these atoms. So the electrons are supposed to be nice and even. They're nonpolar. All should be good in the world. But in the real world, they are in motion. They're in constant motion, just like if I was moving this water across the room. The water's going to start splashing from side to side within the cup, and if I'm lucky, I will not splash it onto my computer equipment. But it will start splashing from side to side as I move it if I'm going to walk across the room. That's exactly what's happening to these atoms. So they are supposed to be nonpolar. They are supposed to be behaving the rules. They're supposed to look, there we go, they are supposed to look like so, but they do not. It doesn't happen very often, just for an instant, but it can happen. And once it happens, you've got electron density on one side of the atom. That makes that side of the atom or the molecule partially negative. The other side, which does not have as much electron density, is a partial positive. So suddenly they're behaving like dipoles when they're not supposed to be dipoles. So here it says occasionally electrons will wind up on the same side of the atom. They're not supposed to. Their parents always told them never do this, but they do just from time to time. And then in that instant, it becomes polar. Again, it's just an instant, boom, and it's done. But it happens. So these are the hardest ones to kind of wrap your head around because they're not supposed to be doing what they're doing. They're supposed to be nonpolar, but every once in a while, for an instant, they act polar. So any questions about anything here? Okay, so good question. So I'm hearing dipole-dipole is referring to intramolecular, whereas hydrogen bonding is inter. Actually, everything we're talking about is intermolecular forces, so we're always talking about going between two molecules. So here's our dipole-dipole, and here it's a force between two molecules. Over here again, we're looking at between two molecules. And now again, we're going to talk about what happens in between two molecules or atoms here. So it's always in between. So inter would be, we talk about covalent bonding. Or you can also think about the ionic bonding as being intra could be covalent or ionic. Does that help a little bit? Okay. It's a tough concept to wrap your head around. Okay. So speaking of tough concepts to wrap your head around, let's see. Does it matter what helium is paired with in the dispersion force? So good question. So sometimes helium could be paired with something else that, well, let me back up for just a moment. So let's say that I have something like, this is our formaldehyde, and here is our helium, and for one instant, we have negative over here, and we have a positive over there, and we would have an interaction between these, and this would be a dipole London dispersion force interaction. So if you had one thing that was a dipole and one thing that was nonpolar, then it would be between a dipole and a London dispersion force. The reason before we called it dipole-dipole was because we had two dipoles. But there also could be a case where we had, say, a helium and we had something like xenon. Neither of these should be polar, and I'm just going to put a bunch of electrons over here. So partially negative, partially positive, partially negative, partially positive. And we see the interaction between the positive and the negative. This is more of what we think of as a true London dispersion force, because you have two things that would not normally be polar. Does that sort of answer the question? Okay, perfect. But it's also true two heliums can have London dispersion forces together, and we're going to see that next. But truthfully, we can sort of mix and match our molecules, and if we mix two things with different forces, then we would have something like a dipole-London dispersion force. So usually I don't go into that much detail in this class, but we always could go there if you'd like. But I think what you're probably most interested in is whether I would test you on that, and the answer would be no. I don't usually mix and match forces. All right, so this is what we call that electrostatic attraction. Remember, electrostatic attraction just means it's an attraction between a positive and a negative. And when you say just helium, do you mean is helium the only one that can do it? So actually every molecule, every atom can have London dispersion forces, and it comes from the idea that anytime, let's say in this case you're carrying water, it will always swing from side to side. Every time you have a molecule or an atom that's in motion, that's what's happening to its electron. So every single molecule and atom in motion, electrons swinging from side to side. It's just we only care about it with things that are nonpolar because they don't have a greater force. So if you've got hydrogen bonding, then the fact that your electrons swing a little bit doesn't really matter because you have that hydrogen bonding. So I like to think of it as we only care about it with nonpolars because they have nothing else to their name. They have nothing else to stick them together, but it actually happens for every single atom, every single molecule. All right, so other questions so far? Okay, so here we're looking at our helium atoms, and here's our very first one. This is the one we talked about. We know that these two electrons swung over to the left side. No real reason. They just, on one occasion, happened to look up and see the other electron and be like, oh my God, we're not supposed to be together, and then they run off, right? Just happened. Well, once it happens to one, another atom seems to do the same thing. It's something we call an induced dipole. So this electron right here starts to feel that there's a partial negative over here, and it's like, uh-oh, there's a negative charge building up. I'm out of here. And it moves over to the other side, and when it does, it creates negative over here. And suddenly they start to pair up and have what we would think of as a dipole-dipole interaction. Color in here. So suddenly they act just like they're dipoles because two of them both started doing the temporary dipole. So helium number 1 has a temporary dipole. The nucleus of a nearby atom becomes attracted and the electron starts to flow to the other side. And again, this is what we call an induced dipole. So helium 1 over here, for some random, inexplicable reason, both of the electrons went to one side. But once that happened, helium 2 did the same thing. It has a dipole now, and it was induced by helium 1. So if you want to think of it as following the leader, once helium 1 did it, helium 2 followed suit. And now these two are attracted to each other. Due to that electrostatic attraction, the positive and the negative. So in helium number 2, the electrons are repelled by the helium number 1, and that's why they swung to the other side. So that's what I drew in the previous slide. You had an electron here, but it moved over to here because it was repelled by the negative charge that it felt. So any questions about this idea of an induced dipole where the second helium became a dipole because of the first one? All right, so now this is what they're starting to look like. Positive and negative that are attracted to each other. Got the electrons on the left side for both of these. So what can happen is you can get a huge chain of these nonpolar atoms or molecules because once it happens to one, it induces it in more and more and more, and suddenly you have this massive chain of London dispersion forces. Any questions on anything here so far? All right, so I think this is a good time to break for our break. So let's go ahead. It's 6:02. Let's go ahead and come back at 6:10.